Okay, let's continue our discussion about imaging. So we have so far visited two labs that do imaging that are in our department, and that is X-ray imaging. And one of them is adapted medical CT, which gives us what resolution at best? So somewhere between 200, a fraction of a millimeter. So 200 to 1 millimeter, depending what you put in there. And then if you put a larger object, then your voxel size will increase, right? So that can be a problem. And then microtomography. And microtomography is basically refers to micron sizes and conversely much larger images that come out of imaging a piece of material in detail with micron resolution. And the best that you can get these days is, well, for microtomography, it's 1 to 5 microns is the most common in geosciences. You can get better, a fraction of a micron, but then it's actually called nano CT. Okay. So what we will continue talking about, since this is quite dominant still in characterization of basically geomaterials, we're going to spend a little more time detailing how these images are acquired, and hopefully because you've seen them physically first, and now I'm going to go into details how images are acquired, that will hopefully click together. That's one point. And the second point is that ultimately knowing whatever imaging you're doing and what are the potential sources of error also makes you understand what you can do. You have to often actually actively design your imaging procedure so that you can actually see what you want to see. And depending on what you want to see in the transport process that you're interested in, you might need to design imaging or work with the person doing the imaging to actually best achieve that. So one example is, great, we know that we can dope one of the fluids, let's say that I have water and oil, we can dope one of them to increase the density difference and essentially make them different under X-ray, because otherwise when I have close densities, I will not see the difference. So now if you inject emulsion, that is a combination of those and has it's a different fluid structure, is that enough? Which phase are you going to dope? So there's some of these designs, like you have to actually know what is happening in the actual imaging device to understand how to design your experiment to actually see where the foam or emulsion is going, as opposed to just one single phase. So you have to understand a little bit of both of details of what you're doing and details of the imaging. So we're going to go into a little more detail on X-ray. So after that, again, we're going to, at 1:15, go and visit Dr. Vincent's lab to see micromodels. So that's our last tour in the department to basically make it a little more interesting and to actually see physically where imaging is happening. All right. Let me do a little bit of more details on microtomography and just developments of X-ray. So again, X-rays are one form of electromagnetic radiation, and no matter which imaging you're doing, you're using one part of the electromagnetic spectrum, and they are invisible to the eye, as is actually most of the spectrum. They have wavelengths that are basically anywhere between 0.01 and 10 nanometers, and the energies go from 120 electron volts to 120 kilo electron volts. They're shorter than UV rays and much shorter than visible light, and therefore they can actually penetrate deeper. and they're comparable to some dimensions of the atoms and a little bit larger than that. So X-rays have much higher energy, okay? And those with the highest energy are called hard X-rays, and they can penetrate solid objects. Now you have heard probably some references. I think Javier pointed to some of those hard X-rays versus soft X-rays and beam hardening during the during the imaging. That actually refers to material reacting differently to different types of X-rays that are composing the beam, and they might attenuate different types of X-rays differently, and we're going to explain that today. So there's soft X-rays. They technically barely penetrate the material, so you don't, especially in geosciences, where for the most part we have 80% of space occupied by rock or the solid material. That's a problem. They were discovered in 1895 by Röntgen, and the images that just do a projection that basically tells you the density contrast, but the projected density contrast of a human body are have been common pretty much since. So they were also at the same time, alongside the medical use, they have been started to use for industrial and research use. But industry and research, they're interested into going into harder materials, and this is where we need X-rays with much higher energy. So just for reference again, harder. Well, where's my mouse? Doesn't seem to be showing up today. I know. Okay, here is the mouse. So basically we have soft and hard X-rays, and these are sort of the sizes. So the wavelength of the X-ray is basically proportional to what you want to see with that X-ray. Okay. So now let's go into this attenuation, because what we measure is attenuation of the X-ray. This is so-called Lambert-Beer's law. The moment I say law, you can assume that there's some simplified linear relationships in there. That is not true, but to the first order it's basically to the first order approximates what's happening. And that's essentially our major source of error. So what we assume is that if I have an incident beam of intensity I0, if it goes through a material, it will attenuate. So if it goes through empty, nothing will happen. There will be no interaction, so I have the same intensity. If I go through a material, okay, there will be a weaker beam coming out. And I'm modeling intensity of that beam as the original times e to the 1 over, right, mu, a coefficient, delta x, which is thickness of the material. And if I'm stacking the same material, then I'm assuming, okay, if everything is perfect, that, okay, I just stack this up and now my delta x is 2 delta x here. So that will just scale in a relatively simple way that way. Okay? So basically I just stack things up. Now, one thing that we have already learned, that the sum of it is that if I filter different wavelengths or energies of the beam, if I have multiple energies comprising this incident beam, then some of them might react with the material differently. So whatever this portion of the material sees is different in nature, just like in composition of the beams, right? Than whatever this part sees, and that can, but I'm making this assumption when I'm reconstructing the image, and that's the source of error. So my model is overly simplified. Our models are always overly simplified. Sometimes it works better than the other times. Okay? All right. So this is essentially what I said. So it's this mu coefficient that I don't know that is basically bundling everything that I don't know into a single coefficient is so-called linear attenuation coefficient. Okay? Now this coefficient varies for different materials. And we're generally assuming that this variation in mu is enough to identify or classify objects of different density, and we will see why. Now, for medical CT, we measure these CT numbers, or so-called Hounsfield units, HU, and they're normalized to air and water, if you remember. Because there's always, you place a little bit of air and water, and you can do that. And because bodies that are imaged for medical purposes are mostly comprised of water, so that normalization, and they are surrounded by air, and we're often doing it in a room, right? So that normalization makes perfect sense, and that's where it starts from. Now, for lab CT and synchrotrons, it's typically intensities or linear attenuation coefficients. They're scaled to some number range. So quiz time, what's the range that Javier mentioned on Monday? What is the range of number of the reconstruct these linear attenuation coefficients? Were they positive, negative? How large were those numbers? In hundreds or thousands? I remember, but I heard it a number of times, so I know. Huh? It's in thousands. So to accommodate that, you don't think, or you do? He mentioned 65,000 as a maximum number. Okay? It's a choice. Frankly, does it matter? You can actually do that. You can go grab some of the numbers, and we will do that a little bit with segmentation. Okay? You can, every image that has 65,000 values, you're still only in one part of that spectrum, and you could scale that image and stretch it to just 0 to 255, which is 1 byte, and then you're also saving memory. Okay? And for the application, recognize you really have enough contrast between two different densities that you're trying to image, or you don't, and whether you're looking at which depends on the CT settings itself more than anything else. If you can visually see the contrast, then you have enough contrast, and typically whether you express it in the numbers that are up to 255 or numbers that are up to 65,000, doesn't matter really. The problem is actually, did you physically tailor your sample, okay, and whatever contrast you're trying to measure in the sample to your X-ray energy, really? Okay. Otherwise, no change of numbers can really help you. That's what I kind of realized over the time. So technically, unless I have a very reason to use all of these numbers up to 65,000, I simplify both memory requirements in my analysis to go to. Okay. So anyway, we're going to do that once we start processing images. We will just, you can, for yourself, figure out, well, does it matter for my application? For some other application, it might actually matter, but for certain applications, it might not. Okay, so it's a certain range of numbers, and again, these numbers, it's very hard to get a very specific reference to what material you're actually seeing based on the number you see. They're scaled, reconstructed. They technically lose the meaning except for this relative value between two neighboring numbers, okay? Relative difference. And attenuation is essentially 1 over intensity. So it's like how much attenuation measures how much I have weakened by going through the material. Okay. Now, what happens if I have multi-component materials? In porous media, we never have only one. That's part of the problem. Do these things just stack up? Well, technically, for homogeneous materials, this can be actually shown pretty well. it's fine. You can just say, okay, this portion is one type of density that results in one type of attenuation coefficient. This portion is a slightly different material with the average attenuation coefficient mu2 and mu3. So I basically just kind of expose. So whatever comes out of here is intensity I0 e to the minus mu1 delta x, right? And that's now my incident beam coming into this material and is weakened by basically the same thing times e to the minus mu2, right? And so you just stack things up, which is nice part about using this exponential function. So I can, okay? The question is also for us, well, if this material within is actually porous material and technically not homogeneous, right? Does this 1 mu1 describe it well? And that can be a problem if you have a medical CT where you are averaging multiple things with it, not just one type of solid and one type of void. Okay. So what happens actually when X-ray shows up or any kind of beam really or photon that hits a material? So here's an incident beam. This is my little squiggle denoting electromagnetic wave, and I have a piece of material here. And if this is a low energy beam, we have so-called photoelectric effect. As I hit the top surface of the material, some of the electrons will just basically be, so these atoms will get that energy in, okay? And I might emit some of these electrons. And they're called photoelectrons. They're basically result of the reaction of low energy electromagnetic radiation with the material. Okay, well, that's called so-called photoelectric effect. What we call mid-air energy, I could have two things. I could have so-called elastic scattering of this beam. It kind of just like bounces off elastically, so to speak, of the material. Or inelastically, and that's where the problem arises. So some of the energy basically stays with the material, gets absorbed, and this some of the energy is bounced off and not necessarily elastically. Okay, and what's bounced, that's called Compton effect. So part of the energy stays in here, and part of it is transferred into this electron that is coming out. And then at very high energy, this is typically not the case for the microtomography applications. Electron-positron pair is produced back. Okay? All right. Now, how do we actually model it? So this mu is somehow modeling all of that, okay, in some sort of average sense. So this mu linear coefficient is sum of the Compton scattering and these photoelectric contributions. We typically don't have positron emission. Okay, so mu in itself is a function of, well, what it is that I'm interacting with, what type of electrons, how many, what their density is. Density of electrons is really also density of the material. Okay, it's related to it, and atomic number, and the energy of the actual X-ray. So some of this is basically the material properties, and energy of the X-ray is another. And it's modeled in the following way. I have rho e, which is electron density of the material, and this is basically a number that depends on atomic number, the atomic weight, and Avogadro's number. So what is my cloud of electrons that I'm interacting with? And then I have a coefficient A, a coefficient B. Z is atomic number to the 3.8. This 3.8 and 3.2 and energy to the 3.2. These are something that has been over the years of measuring and modeling, okay, has been agreed, meaning that there's at least 20 papers disagreeing, right? Agreed to, but it's ultimately for all of you who have done the curve fitting, this is a curve fitting problem of sort, except that I'm trying to fit that I don't know what the functional relationship is. So I have to keep trying. Right? Every time you're actually fitting your measurements, you have to have an assumption about what the measurement is, but you have to do the measurement in order to come up with a functional relationship. And basically, you can see that I'm inversely proportional to the energy and atomic number. So depending on the energy, right, if I have low energy, I'm going to be dominated by this z to the 3.8, and this number will not be all that important. And for low energy, we also know that we mostly have photoelectric absorption. And for higher energy, where we do have Compton scattering, then you're controlled by this electron density. Because if this is high, then this is kind of averages to a constant of some sort. Okay? And you're mostly controlled by this. But again, these are the things that you don't know. Again, there's Z here as well. All right. So how do we now reconstruct? When we actually refer to tomography, okay, tomos is to cut or to section something, and to write is to graph or graphate. So this comes from Greek. So basically, it takes multiple projections in tomography to actually reconstruct something. So this is where the computed part comes. So when we refer to CT, it's not just tomography, it's not just an image that I got as a result. I have to take all of those images and compute something to reconstruct a three-dimensional image. Okay? So that's what CT part refers to, computed tomography, right? And sometimes like it's CT, XCT, CMT, XCMT, X-ray CT. No, there's all kinds of alphabet soup of all of these, and there's no such thing. I tried to look for an agreement. There's no such thing in agreement. There's 4 or 5 of these that float, and different people use differently. You could also often see micro CT. So there's CT. Both of the labs that we visited are CT, but one of them is micro CT, which refers to micro. So in any event, all of that works. So basically, this is my just one projection, and this is actually a reconstructed three-dimensional model. So in this case, it's obviously medical things. So what are these? Ribs. Suddenly I'm hungry when I mention ribs, though this is actually a person. Anyway, I'm cutting through. Is this heart? I did not. My biology class was long ago. Anyway, so, and this is a three-dimensional heart that you can reconstruct from some of these images. Okay, so this is what a three-dimensional image does. So again, CT, computed tomography, sometimes also computerized axial tomography, computed microtomography, also sometimes this micro CT, or which micro in Greek. So all kinds of versions are in there. So what we really get as one of those projections, and this is what a version of this is what you saw by Javier demonstrating. One of these projections, okay, that shows up. But it's from these projections and going around an image that you reconstruct a cross section through a bead packing, for instance, here in this particular case. Okay? And so you get, these are basically orthogonal cross sections of a three-dimensional structure, right? So we get these from these, okay? And this is this computed part. So this is just a radiographic image, okay? And where you have a lot of absorption, that's where you see dark. The one we saw was a sandstorm, so everything was dark. There was not even a hint of some interfaces or anything. It was just dark, right? And that's because it's just much denser image. And this is an actual reconstruction image. And we still see this. So this is now, whether I see my solid as a dark or light is a matter of choice when you are mapping these numbers. You can always flip it. to your liking. So sometimes it's the voids that will show as dark, and sometimes it's the solid. When I plot, personally, again, it's a matter of choice. I personally like showing solids as black and empty as void. But that's opposite of the actual spectrum, because empty is typically white, which is 255. It's a higher number. And dark is 0. Okay. So in that sense, it's a matter of agreement. We always make sure to say what it is that you label things with. All right. So geometry in this reconstruction is important. How do your beams interact with image, and what is the... So this is sort of a parallel, not sort of, this is a parallel beam, okay? So, but I have to have a source that is emitting a parallel beam, right? And I have to maintain a constant density across this, which is not necessarily easy, right? With respect to the size of what I'm imaging with. So then I'm passing through, and here I'm reacting with a detector, and this is where the image is formed, okay? Because I have something that is sensitive to those beams and creates an image. And then I rotate, and from a different direction, I get a different image. Right? Now, I basically impose a grid on top of this. And if it's easier to pose these equations and calculate if this grid is kind of parallel to the beams themselves and orthogonal to them. Whereas in this conical case, I can see that sort of like if I pose a regular grid, then beams are sort of like cone, like they're denser here than they are here. Right? So that can cause slight changes in reconstruction, of course. So this is when the source is a point source. But of course, point source is kind of easier to execute in the lab. Okay? All right. So I have to know what the geometry is. The point I'm making is just that it's important what geometry is. Yes?
So for the family projection, can our grid be like not a square grid? Smaller on top and not bigger on top? So when
Yes, I mean, that's just like, look, we do these changes constantly. If you think about Velbor, it's always cylindrical, right? And you're fanning out radial geometry. And as you're further away, your sort of numerical cell has much higher area than it does closer. And that can cause trouble in any kind of going back and forth. What do you do in between? Interpolate. What you don't have, you interpolate. You always have like information just like it's sort of, it's going to cause a little bit of trouble. And what also it matters is how you get magnification and better resolution. Also basically depends on placing this image closer. Like what you have to play with is you have this distance here and then relative distance of the object to the source versus detector. Just like you do when you're shooting with the regular camera, right? There's the object versus with the understanding that the light is sunlight that comes from somewhere. So that's essentially the geometrical aspects that are then important in what is the type of magnification that you can get. Okay. Or can you actually place something in between those objects to magnify? Anyway, so when we have a projection, let's actually look at this. So basically, let's say that I assume I have X-rays, and I have a much higher density object here within this object, right? Then my X-rays are going here. So here, as they're going through, they're basically not seeing any objects. So there's no attenuation. Now here, there's a little more attenuation. There's quite a bit here because I have both a denser object and part of this lower density object, assuming that I have higher density in yellow. Right? And then when I avoid yellow part, I'm going through majority of this object. So how much I attenuate in the end at this portion here depends both how much material am I passing through and what is the density of the material that I'm passing through. So it's a combination of both. And then I get that projection here. Okay? And then I rotate slightly and I keep doing that. So as this object is, there's this sinogram that is basically obtained. So if I have an object here, that object is somewhere here, they say. Okay, so my object is here. Okay? So this is where I have lighter colors, darker colors in this projection. Lighter colors, darker colors, and this is this one line. As I'm rotating, so then I rotate a little bit, and then I'm gonna get this other line, and I assemble as I go through. So here is a visual. If this video wants to play, whoops. Okay. So basically, there's one image on the right that will have only one object. Hopefully, getting there. All right, so this is my rotating object. This is this sort of disturbance in the image and how the sinogram builds up. Let's do this again. And then multiple objects are on the left, so I'm going to play it. So this is with multiple objects, and this is the sinogram that you get as you're rotating. And why you didn't see that in the demonstration yesterday is that most of it was sandstones. It was at this projection level, it was all kind of homogeneous. Okay, even though that sandstone is a mixture of voids and solids are highly attenuating and voids are not at all. Yes. So that's this. What is the level or resolution that you have to see the details? Now, you will typically, this is a typical sample image. You have some background in there in your device. So you will also do just one image without anything. And that was that normalization that was shown by Javier. So he had one image, put the mount out, do the background, right? So that's called a flat field image. And then you can subtract the two. One can also obtain dark field image that is measured just without any X-rays. And then you get this normalized, this is your sinogram that is normalized, sample minus dark divided by, so sample minus this divided by this minus this. And those are this normalized intensities. Okay? And that kind of, you can see then how different types of settings give numbers that ultimately in absolute sense mean nothing because they're normalized coming out. And then you can project this onto whatever. Oh, do I want 0 to 255 or do I want 0 to 65,000? All right. So math was actually worked out by Johan Radon in 1917. It's just that technology didn't necessarily catch up immediately in terms of reconstruction. So for solving this, so that kind of died out until 60s. And Cormack rediscovered the methods as well as Hounsfield. Now some of these units we call Hounsfield units. And it's the two of them that actually shared the Nobel Prize in 1979 for the development of tomography. So this part of this, like, okay, somebody has discovered how to do this, but since it couldn't go into application, it kind of died out. And then somebody had to rediscover. This is pretty common for technology, right? We've known a lot about nanotechnology in the 60s in terms of just the theoretical development, but couldn't execute it. And today we see a lot of devices that are basically applying nanotechnology. So he was basically trying to figure out what's inside of a sphere by imaging it in his reconstruction in a very simplified way. Let's say that I have a super simplistic image and I have a parallel beam and I have only two voxels across. And let's say that I have four materials or some sort of, on average, attenuation here is 2, 4, 1, and 3. How would I try to get or find these numbers? As I'm passing through, okay, attenuation through these two, basically, is mu3 plus mu4 is 3. I have that e to the minus something, but you can simplify it to this, okay? So basically, mu3 plus mu4 is 3. Mu3 plus mu1 is 4, and that's what 6. This is what you're measuring here when you get an image going through here. You get 6 and 4. Yes? This projection. This projection is 7 and 3. And in this simple geometry, I have beams that are parallel to my coordinate system. So it's a very simplified case. So I'm going to get this set of equations that I solve for mu1, mu2, mu3, and mu4. And in this case, I have 4 equations and 4 unknowns, so everything is good. I could add one more this way, right? And I have to understand that would now, I am going through more of material in this direction, and that should be accounted for. And if I have curved geometry, then there is even more trouble that way, right? So technically this way, I have the length of square root of 2, the square root of 2, right? That should be factoring in at this degree. So this is where, but then I'm going to have slightly overdetermined system. I could also add the fact that I do have air or something on the sides of the sample that helps in this reconstruction to anchor. So this is how these projections look like. So let's say that I'm imaging a sphere. If I'm imaging it just with 2 projections, I'm going to see a square instead of a sphere, right? Because I just don't have enough projections, and this is going to be just a square object. So as I keep adding more projections, so this is 4 more, 8, 16, I can so this is non-filtered, this is a filtered image for to correct some of this point spread. I will get more and more around for that same sphere. Okay. So this is an effect of how many projections I have and how much resolution I have. Okay. So today what we really kind of care about, we let Javier play with all of this details, and we just want that image at the end and then deal with the images, which is not always easy, because which is why I say it is important to know a little how did that image come about, so you know how to deal with the noise that come in there. Okay? So a single reconstructed volume can vary in size from 0.5 gigabyte to 16 gigabyte, depending on resolution. I'm having now, I'm seeing uploads to DigitalRocks portal that are easily 1 terabyte, because it's a sequence of images, and each image is. So I asked people to actually section the entire thing into sort of 2 gigabyte increments, right? So that it's more easy to manipulate or download or work with. So this is a processing, storing, backing up the data locally requires some sort of resources. So unless either Dr. Espinosa or Dr. DiCarlo delete their data from the local machine, they're not going to be able to continue imaging. Okay? So in that sense, they have to store that data somewhere else. So if you're a facility, question is, what type of contract do you have? That's something to think about, because you give an image back, is whoever you're giving it back counting on you being able to retrieve that image later? And if so, then you have to figure out the backup and storage and how you do so effectively, and can you easily then post it on some FTP servers for people to download. Right? So that's something that one has to figure out, and this is partly a motivation for me to start building that DigitalRock portal repository, because I realized in my own practice, as I'm moving around, I don't know where my images are. I want to post it somewhere online where I can find them, and when people ask me, hey, can you share images? I can say, just go to the DigitalRocks portal, right? It's there. So I don't have to go find it. Which computer is it on? How big is it? Can I easily share it? Those become, like, you can't email something that is 16 gigabyte easily. So, okay. So those are things to think about. Now, we have to understand that these pixels and voxels, they have sort of a finite volume. I'm averaging over that volume. So there is, of course, errors in that. So in imaging human body, I will have sort of like a thickness in these. In CT, we have seen you can choose where you're going to do in Z direction how big of a spacing you're going to be. But then you're technically, when you get an image here, you're averaging over certain thickness close to that. And in between, you don't have values. And if you need to fill them in somehow, well, you fill them in somehow. Okay, so the world is actually kind of pixelized like Legos. It's not perfectly smooth, even when visualization shows that it is. Okay, so visualization can, post-processing can smooth these things out, but that's essentially interpolating data that is in here. Okay? So if you do interpolation, you can smooth things out. Yeah. So again, there's this partial volume effect. So sometimes, like, let's say that my pixels are like this. I will capture, this is sphere, 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 blob of air, water, water. Okay? So this pixel here, if I actually either downsample this data, I'm going to average 3 different materials here. And that's the reality. If my pixel length was actually this. This image obviously has much more detail because I see all of the detail. But I can already even see on this interface a little bit of this pixelization happening. Right? So that's something that is always there. If you have a number of different substances, they are, you know that you have 3 of them, okay, in here. Here you have 2, here you have 3. But when you're reconstructing and in different fractions, and you don't know those fractions, right? So when you're averaging, they're all playing out sort of in a nonlinear way to give you attenuation coefficient of this entire box. And the more interfaces between different materials you have, that's another thing, complexity of the material within. The more interfaces you have, more of those scattering effects and attenuation you're going to have. And that can cause issues. So just understand that, yes, the images that we see are better and better, and they're crisper and crisper, but there's always a little bit of this averaging and partial volume effect built in, and certain simplifying assumptions that we make. Okay, I think at this point we will actually, well, great, stop, look at that timing. So after that, I'm going to just overview a little bit of X-ray systems, but we have seen some of them already, so that should be easy. But now we will stop and see some micromodels.